Good afternoon, everyone. I want to thank Aapresid for inviting us and you for being here. Today, Pablo Hernandez, who is a founder member, will talk about our company. First of all, to speak about the impact of consolidation or compaction, what are the tools we have for diagnosis, and what are the main causes and the practices that we carry out for the proper management of this problem. Pablo will now give his speech, and then we will have a Q&A session. Good afternoon, everyone. Once again, thank you for being here and participating in this event. Thank you to Aapresid for inviting us. Our subject today is soil compacting, which is a problem that has been worrying all producers, and we know it's one of the causes when it comes to less yield, and that's why we want to explain what it is and what we're working on. It is a growing problem in modern agriculture with significant consequences for the health of the soil and agricultural productivity. We want to see the impact of this on the soil health, exploring its causes, the methods for diagnosis, and better practices to handle it. The compacting with the diagnosis and best practices for sustainable management is a phenomenon that affects the structure of the soil by diminishing its capacity to bear the growth of plants and the flow of water and air. It is a common problem in agricultural and forests lands, and it can have significant consequences in the productivity of crops and environmental sustainability. We're going to see what it is, the factors that generated the methods for diagnosis, especially the easy scan method, and the strategies for mitigation of these effects. So, specifically, what we see in compacting is the densification of the soil particles that are pressed together, augmenting its density, and this impedes the normal infiltration of water, the exchange of gases, and it diminishes the production capabilities of the crops, and it affects the biological activity of the soil. The main factors that we see that can affect compaction, they always have to do with management and the intervention of men on the countryside, the traffic of machinery, repeated trafficking with heavy machinery that augments the compaction, inadequate tilling. There is a problem that we don't see that often, but it's one of the factors that in plots that we have been seeing when there's a lot of non-tillage. After 10 or 20 years, you can still see that problem there. Intensive grazing and the degradation of the soil with low levels of organic matter and with low nutritional levels when it comes to calcium, magnesium. They began to acidify, and we know that it's not just something to do with the physical side of soil, but it complements with chemical problems as well, which make a soil more susceptible to compaction. The diagnosis, as I was mentioning, is easy scan, which allows us to determine the characteristics of that soil. Here, it is a scanner that goes on the truck, and what we do to achieve this is the scanner goes through the plot every 20 meters. It does parallel runs, and it emits electromagnetic inductions, and they reach 1.10 meters in depth, and it can determine the problems and the benefits of the soil. It can obtain the capacity for electricity conduction of the soil, and it can also read about organic matter, water, the presence of salts, altimetry, etc. So it can analyze, and it can see the different textures, and it can show us the areas that are more susceptible to compaction in the plot. So when we have this information with electromagnetic induction, we can determine the depth at which they find alteration in the soil. And that alteration that receives that electromagnetic induction may be associated with a change of horizon when there is a change of the texture of the soil or the density of the soil. So that will give us information and a map of the features of where we have greater susceptibility for compacted soil. So when we finish with the scanner, we have different productive potentials and we get different features of the soil. I'm going to talk about this. These are very similar. There was no interference here in the different TV horizon or tuff. So we can see it's pretty similar from 20 centimeters to 110 centimeters, but we can see the differences in potential when it has to do with the altimetry, water storage, organic matter, and these factors determine that if we fertilize it all the same and plant it all the same, you can see that the red and yellow has a different production potential than to the green side. The scanner gives us other information, altimetry map. You can see the green area, which is related to the area of low productive potential. A stored water map, which tells us the volume of water that there is there. We can determine the useful water rate so that we can determine compacting. If we say that we have compacting or dry soil, you can see that we have 16 millimeters here, and then in the high productive potential, there's about 80 millimeters of water. So the accumulation of water is totally different from one to the other, so the soil resistance will be different as well as the productive potential. This is the map of variation in depth. It tells us where the scanner found an alteration associated to texture changes in horizon. And in this map, we begin to work with penetrometry, and we can go to strategic places where the scanner has generated that information and determine in zones whether we have that problem or not. Something that we've been seeing often is that there is compacting in plots, but not always in all plots. So there are some plots where the problem is very much localized and you can focus the corrections by sectors. This plot shows us that between these centimeters, it found an alteration, and therefore that information of such little variation at depth shows us that independently of the colors of the localization, we will find compacting problems. On this, we work on when it comes to the chemical side, we do a sampling that is every so many hectares. We analyze phosphorus, organic matter, pH, and altimetry, and the nutrients. And we can see that the basis for exchange when it comes to calcium, the CEC, we can see that these nutrients are lacking in the soil and they are fundamental for its structure. And at the same time, it allows us to add layers of information to see the productive potential and how it is affected by certain nutrients. Here you can see the pH, the electrical conductivity of the soil. You can see here the low productive potential with very little electrical conductivity due to the excess sand, organic matter. This is what we've been seeing the most. And as I was saying, when we talk about soils, the difference of productive potential and the susceptibility to compaction. We can see here two areas of gray. You can see the organic matter in the darker colors and 1.6% of organic matter in the same plot. In these areas, we are between 3 and 5% of a percentage of organic matter. And therefore, this is a plot that when you see these features, physical and chemical, you can see that the productive potentials are completely different. Having the technology that we have allows us to make efficient use of the inputs, not just looking after the environment and being sustainable, but also maximizing production and getting better yield per hectare. The same with phosphorus. As you can see, we say that within the same lot we have between 6 and 29 parts per million. So when we talk about nutrients within a plot with today's technology is something that we need to determine in each part of the plot what we have available and work from there. Penetrometry and compacting diagnosis, which is the second phase of the diagnosis. Penetrometry is a method of diagnosis where through a plunger exerting pressure, we will be able to see at what depth we have compacting or not, and what the resistance of the soil is. When a soil has more than 2 megapascals of resistance, we are in the presence of compacting, and that would determine that roots don't have enough strength to be able to go through that layer. And therefore, if the roots can't go, the capacity for infiltration of water is less, the root capacity is less, and therefore the final result that we will get will be less. The second phase, when we begin to work on the maps of the variation of depth that the scanner showed us, that between 10 and 25 centimeters, between 19 and 23 centimeters, we had some alteration with the penetrometer in these graphs. We can be shown the depth at which we measured the resistance of the soil from 0 to 60 centimeters, and then the resistance of the soil in megapascals, where it shows us that we have a resistance of over 5 megapascals up until 25 centimeters. And once the penetrometer goes through this layer of resistance, the resistance of the soil completely changes. And therefore, that compacting layer is the one that is affecting us and diminishing the capacity for filtration, and we must work on that once we get the diagnosis of how to solve this problem and how we will continue in the future. Something that we evaluated when it comes to the impact of compacting, that is, comes through the bad management, mismanagement within the plot, and that it is man-made, because when we analyze the penetrometry underneath the fencing, it is the same characteristics, the same kind of soil, but not done by man. We see that under the same conditions, they are under 1 megapascal of resistance. And when you go to the limits of the plot, which have been compacted continuously, we can see that we are over 4 megapascals. And therefore, what we can see here is that the plot itself has compacting features that are similar to the most problematic areas, which are the borders. So what we've done so far is to get a diagnosis, and I believe that is crucial, because many times we get to talk to a producer and they all have paratil, and immediately you want to borrow it. And what we can see is what is important is to have the right diagnosis, and from then on to see how you will manage the problem. But at the beginning, you need to have the main information, which is the diagnosis. The advantages of EC scan for soil management is the combination of electromagnetic readings, maps for hydric retention, water retention capacity, depth and soil density maps, complemented with the data with the penetrometer that offers a comprehensive vision of the state of the soil. This allows the optimization of agricultural production by identifying areas with different productive potentials and adapting the practices to the specific needs of each area, improving the efficiency of the use of water based on the capacity for water retention in the soil, and to implement corrective measures, corrective steps to mitigate the compacting of the soil, improving the health and productivity of the soil long term. This is important because many times it happens that in plots you arrive at the countryside, and when the producer sees that and you do the diagnosis, it is not compacted. That is important, therefore, because many times there are tillages that makes no sense due to fashion or trends. The plot itself doesn't need to be compacted completely. And what are the management plans to improve compacting? And this is where we see all of the management that we just saw when the plot is not totally compacted due to man-made practices and the practices that can help so we don't repeat that mistake. This is the rotation of crops, incorporating within the plan cover or service crops, not to leave them on their own throughout the winter, but to put not only service crops, but also multi-species crops that can give different root systems to help the structure of the soil, minimizing machinery traffic, to begin to work with controlled traffic within the lots, mechanical till, like paratill and subsoil. Whenever you speak about this, it is important not just to say, let us uncompact the soil, but also when will we do that, at what time of the year, what will we do afterwards. What we've been saying before when it comes to the basis, we see there's lack of calcium, there's lack of structure. So if you decide to mechanically correct that without doing the chemical correction when we have that problem, in the short term, you'll go back to the same problem. We see when it comes to soil degradation or lack of fertilization, so the right management of fertilization, the rotation of crops, and the adding of organic matter will help with compacting. Coming out of the physical side, but in order to help understand the degradation of the soil that we've been seeing and how the chemical part actually negatively affects soils, so they are more susceptible to compaction. This is a graph over 8 years of lab results where we started analyzing and seeing the problems that lie in the factors that help to diminish the soil's structure and their capabilities. And we could see in the year 2017, we analyzed 3,500 samples, and up till now, it's 4,000 samples. And we see that there is a marked acidification. This is throughout the country, actually. It's not statistical data, but just for us to see a trend of what's happening with our soil. In 2017, we had 6.52 average pH over 3,500 samples, and in 2024, we have 6.25 as the pH average. So we can see that they begin to acidify, and when we go to the high productive potential, everything is below 6. So these are alerts and red flags that we should take into account. In phosphorus, as you can see, we were in 40 parts per million average. Today we are in 18 parts per million. The relation between calcium and magnesium, which is something we've also been seeing, the structure of the soil, we had a relationship of 3.56, and now we are in 2.67. And something that's very important as well, whenever you speak about potassium, that is a nutrient that is in excess and we get no response, is still the same, but actually we've gone down from 1.686 from 2017 to 1.43. And if you go to high productive potential areas, you can see values of below 1.0, and calcium in CEC, it's gone down from 52.10 to 39.62. So there is a negative trend. Soils are being degraded. If we don't start doing the right rotation and the right fertilization, we will have more and more problems as the time goes by. And this is just to show you the analyzed samples and the fact that the problem is becoming worse as time goes on.
When we analyze the parameters, look at the pH from 6.52 in 2019 to 6.25 in 2024. There is a 5% difference to improve the pH levels. These are large amounts of calcium, magnesium that one has to contribute. So these are red flags that indicate that we have to take action. As regards phosphorus, we have lost more than 54% the high yield potential and genetics. We have a higher production capacity as long as we have water, and fertilization with phosphorus are some of the measures. So when we have 50 quintals of soybean, and to start with, we have 50 kilos, we never recover what we are extracting. When we look at potassium, it's good to take this into account. For the past 8 years, we have seen a decline of 23%. These are more trends showing the same kind of problem. And going back to the soil structure and how compaction has an impact in the calcium-magnesium ratio and the cation exchange capacity. That acidification and lack of calcium that renders weaker soils enable more rapid compaction. When there is mismanagement in terms of fertilization, we will also get, as a consequence, compaction. I will show you different experiments we have been doing, different tests to determine the impact of compaction in water infiltration resistance of the soil as measured with penetrometry, and we have measured the penetration of water in compacted versus non-compacting soils. We have done a double ring methodology with infiltrations at 25 millimeters, 50 and 100 millimeters. We have done a measurement of useful water before the test. We analyzed the texture of the soil. We determined the time of infiltration for each type, and subsequently a new penetrometry in humid and dry soil, and then we did the trial pit. And this essay was conducted in Córdoba. This is a lot that we had already identified in 2022. We recognized there was a compaction problem there within the same lot. We had identified one compacted area, which is signaled as area 1, and a non-compacted area marked with number 4. So we decided to do the different studies here to compare both areas. When we did the study in 2022, in point 4, there was no compaction and the resistance of the soil was continuous. In point 1, there was a point of resistance of 0.5 megapascals, and the soil did not evidence any problems. So we did an infiltration at 25, 50, and 100 millimeters with a double ring method, and we measured the time of infiltration at each of the locations. Then we did penetrometry in the dry area and then in the humid area, and finally the trial pit. Before the infiltration, we determined the useful water we had at 60 centimeters. In point 1, which was compacted, we had 27 millimeters of useful water before the test, and at point 4, we had 44 millimeters of useful water. This difference in compacting shows the capacity of storing water of the two types of soil. In the lot, we also analyzed the texture of the soil as part of the same lot. When you start looking at the details, you can see that the texture is not consistent. It is very important to determine the texture. In point 1, which was compacted, texture was loamy, sandy for the first 20 centimeters, and at higher depths it was sandy, but the texture at a depth between 40 and 60 centimeters, in point 4, it was sandy loam. I'm trying to get it to work. Okay, I was trying to show how the infiltration was done. So, what are the conclusions? In point 1, which is compacted, here we have a chart of the millimeters of infiltration by time. In the vertical axis, we have time, minutes, and we have the millimeters infiltrated in the horizontal axis. We see that in the compacted soil, to infiltrate 25 millimeters, 12 minutes were required. In the soil that was not compacted, only 9 minutes were required to infiltrate 25 millimeters. As regards 50 millimeters, 50 minutes were required in compacted soil, and in the non-compacted soil, only 38 minutes were required. So we are simulating rainfall. If we have 50 millimeters rainfall, in 50 minutes, there will be infiltration in compacted soil. And how about 100 millimeters? We need 123 minutes in compacted soil and only 84 minutes in non-compacted soil. So that difference in the capacity of infiltration will determine the yield based on the water we have. But this is a problem we are facing where we have runoff and different problems. It is important to understand that the capacity of infiltration decreases by more than 30% when we have compacted soil. At the level of infiltration, we did this trial pit. We determined how infiltration at different depths had worked for the compacted and non-compacted types of soil. So 25 millimeters, 50 millimeters, of 100 millimeters, regardless of the measurement, the infiltration shows differences. And when we evaluated the distribution of humidity and the depth in the soil for non-compacted soil, for 25 millimeters, 31 centimeters were infiltrated. For 50 millimeters, 42 centimeters, and for 100 millimeters, 54 centimeters. So infiltration was 70% more for non-compacted soils compared to compacted soils. This capacity of infiltration is fully associated with the root capacity of plants to absorb nutrients, and it is also related to the final yield. When we analyze the penetrometry, it is important to understand whether the soil is dry or compacted. When the soil is dry, but we have compacting or compaction, the resistance in megapascals will be high, but resistance grows up to a certain point and then it decreases as it goes deeper. So regardless of whether the soil is dry or compact, the charts show the trend of compacting. How about water being added to that kind of soil at the different amounts shown above? Compacting continues to be marked between 15 and 25 centimeters. So the water helps the soil decrease its resistance, but compacting is still marked at the same depth. So the ideal thing would be to do the penetrometry at the field. It is important to understand how the soil has resistance, but once you go deeper, that resistance no longer holds. And even though the soil is dry, when there is compacting, resistance is continuous. When you go to the field with a spade and you cannot go deeper than a certain point, the probe or the spade will go deeper without any problems when a certain depth is exceeded. Now we will see the implementation of mechanic tillage to reverse problems of compacting and the detected depth. This is an experiment we did this year in 2024 in the northwest of Rio Cuarto in Córdoba. This study, in 2023, we had scanned the lot. We found compacting problems between 11 and 16 centimeters. With the penetrometry, we detected compacting between 15 and 25 centimeters. So the idea was to have a paratill working with 25 centimeters of depth, but only for half of the lot. We knew that the entire lot had this compaction problem. So the green area is a green where no tillage was applied. In the red zone, the paratill was used at 25 centimeters depth. Then we planted maize. This season had good water conditions, and the yield was on average 10,000 kilos. And we evaluated the result or the yield where comparing the area with tillage and without tillage. With no tillage, the result was 10,000 kilos, and we see that the result of decompacting when we have problems, the difference or the total difference was 10,061 kilos. So we knew that there was a compaction problem, and we were able to analyze these parameters. After that, we determined the time of infiltration in the area to understand what had happened. This is fully sandy soil. There is organic matter, it is very light, and in the compacted zone to infiltrate 25 millimeters, I only needed 9 minutes, but in the areas without compaction, only 3 minutes. This is fully sandy soil with a high capacity for infiltration. For 50 millimeters of water in the compacted area, 39 minutes were required. In the non-compacted area, 21 minutes. And for 100 millimeters of water, 58 minutes in the compacted area and 43 minutes for non-compacted areas. So for maize crops, we were analyzing the capacity of infiltration in the soil, and this determines the difference in yield for the crop. Having performed the harvest, a penetrometry was performed to determine soil resistance after the maize crop. This was a very good crop, but the crop does not create decompacting. The soil continued to be compacted, even though we got maize for more than 10,000 kilos. This is a crop that grew with good conditions and yielded 10,000 kilos, but it did not create decompaction. We conducted a penetrometry again, and we saw that the resistance of the soil with 100 millimeters, there was no resistance. So vertical plowing or vertical tillage rendered good results in this season. The idea is to continue evaluating this in the future to see how it performs after 2, 3, or 4 years with vertical plowing. This is another area in the center of Córdoba. The lot has a high yield potential. We started to see this problem with differentiated areas Some of them were highly compacted. The scanner shows, and this is the benefit of this diagnosis. It helps us determine the areas where we have compacting problems. And then another area where there is no compacting problem. So we start to see that the high-yield lots, where we start seeing more resistance of the soil, these are in the areas of higher yield potential. This is associated with high yields. We have more intensification of transit, and there is more humidity during harvest. So stepping on those places or treading on those areas is beneficial. And we see that there is an influence of compacting here and more influence than in those with less compacting. When we conducted the study, this is the problem that we found. The previous crop had horizontal roots. We decided to apply vertical tillage. Half of the circle was planted with soybean and the other half with maize. We need to show this because these are the results. To decompact, to plant soybeans, we are not helping the system to have continuous improvement over time. We are just obtaining immediate results for this season. But look at the problem. The problem existed because when strips were left without tillage, the capacity of the root exploration showed results of compacting. But in the long term, it is not correct. In the same circle where half was planted with maize, where there was no action taken, it was a flat root, and it's very different from the kind of root we get in the area where there was vertical plowing. This is another area in Rufino, another plot. We had been doing a study for a couple of years. We started the diagnosis in 2022. We identified that there was a general problem throughout the lot. The compacting was remarkable, above 4.5 megapascals, and we saw a low level of calcium. These are pH levels. The calcium and the cation exchange capacity was between 40 and 45%. It was not saturated with calcium. In this lot, the producer decided to leave a strip of 50 meters without any kind of tillage. This is an image that shows the effect of the crop, and it shows perfectly well where no tillage was performed. During the harvest, we obtained a yield map, and we filtered the result, comparing the areas with paratil and the areas without paratil. With no paratil in the 2022-2023 campaign, the maize had a yield of 8,993 kilos. In the area with paratils, it was 9,907. And we did not evaluate variable handling, but the degree of compacting. For paratil, the producer assigned it or allocated an expense of $20, and the result is that 914 kilograms extra were obtained.
When you think about the price that the maize was sold, there was a benefit of 163 US per hectare by dealing with a compaction. This year, soybean was sowed with what we were doing last year. To look at the image of the soy in January 11th, 2024, it still has that line where no tilling was done, and soy gave between an average of 4,000 kilos, and where no paratill was used in 2022, the soy yielded more tons, and that went without the non-paratill. So with paratill, it had 4,400 kilos versus a lower amount, and in soybean it gave us an amount of 230 kilos in the second year of paratill. And when we did this with these costs, we had a cost of so much per hectare. We're seeing here the implementation of service crops by trying to work with a biological decompacting. And there's different ways to work on this, not just thinking about mechanical decompacting, but there's also biological decompacting, which is a right complement to begin to work in order to get compacting long-term and not immediate. This is a trial that we carried out in Córdoba, in Pozo del Molle, in this particular lot. What we did, or what had been done before this, was areas of penetrometry with a block of 25 hectares. We had determined that we had a very well-marked problem between the 10 and 25 centimeters, and what we did here was to implement a multi-species crop cover where we had vicia, veg, we had rye, we had radish, and rapeseed. And the idea was to have different root systems to help improve the structure of the soil that would give a contribution biological and to help biodiversity of the soil to improve its structure. And that was the effect of these succulent and thick root systems that allows us to improve the capacity for water retention and filtration in the soils and to deal with the compacting in a biological manner. Helping with this compacting problem, once this service crop was done, we sowed maize. We again checked it with a penetrometer, and we could see that the soil resistance was 2 megapascals or less than 2 megapascals. And we could see in this particular plot that the resistance of the soil and the hydric conditions did not have any compacting problems before sowing the maize. We sowed it, and over that we got the yield map. All of the blue is the plot with a multi-species crop, and you can see in the yield, you can immediately see where we had that problem. And when we filtered the information, we determined that where we did the biological decompacting with rapeseed, rye, and radish, we could have 8,434 kilos. And in the trial, where we also used a service crop, which was just rye and veg, we had a yield of 7,536 kilos. So with multi-species in this particular plot, we had 898 kilograms difference with the management of multi-species versus a normal crop of veg and rye. So we can see that there is not just one way to manage this, but you must really get to know what is the problem that we have. Within the conclusions, we know that the main thing to begin with this is to do a diagnosis. A precise diagnosis will help us to really go out into the field and to evaluate the problems. That will help us make decisions to deal with the problems. Then you'll have to see whether it's mechanical, biological, or chemical. But it is important to have the right diagnosis first, infiltration and penetrometry, more time in compacted areas and less distribution on the profile. That means that the infiltration is less and the yield will be less, as well as the root development. We know that there is no variation of compacting by giving more water. If you see compacting and you say when it rains it'll be gone, and what we have assessed is that it doesn't happen. The soil, if it is compacted, it will continue to be compacted no matter what the rain is. And then nutritional detriment and its implications, the diminution of chemical parameters continuously from 2017 to 2024, the deterioration of the soil structure, the relation of CEC. We can see that the mechanical decompacting with vertical tilling, when there is a problem, is a solution. We can see that the solution needs to be accompanied by management. There is a significant amelioration of structure and the capacity for water retention and more yield in May and soybean later on. And with the biological decompacting, these service crops allows for the betterment of biodiversity. So there's general benefits and recommendations, the importance of continuous monitoring and the integrated management of soils, the need for sustainable strategies to keep the health of the soil long term, to reinforce and improve the nutritional plan of soils with efficiency and awareness, precise diagnosis with the right management of soils in order to rise productivity and environmental sustainability. Thank you very much. This is what we had, and we've been working on this. Any questions? We are here. Thank you.
Buenas tardes.
Good afternoon. When it comes to compacted soil, there is a relation. There is a low CEC, whether it is biological or mechanical, this compacting. Do you think it is important after this decompacting to use dolomite to contribute calcium and magnesium, and also to work with fertilizers or nitrogenated like diamond or something like that, and not to use urea so that the soil doesn't acidify more? Do you think that is important, that you use that management technique? What we see is that in these soils, when we do the diagnosis, we know that there is a low percentage of calcium or acidic pH. Before we do the decompacting, it'd be great to incorporate these calcium products such as calcium carbonate or dolomite, and that will help to incorporate calcium and magnesium by using calcium sulfates. And this will give us magnesium and calcium within the system. If the soils are acidic, it's better to put carbonate to be able to neutralize pH, and in high productive potential plots to use fertilizers that have ammonium nitrate to replace nitrogen as urea, which acidify the soil, versus products that are neutral or where acidification is minimal, will help to counteract these problems. I want to ask another question. In the plots where there is watering systems, there is oversaturation of calcium carbonate. And I have also noticed that in those plots with calcium carbonate or oversaturation, there is compacting as well. And I've also noticed that in those plots that there is a high relationship of calcium and magnesium, but it is calcium that it is as a carbonate, and there is compacting. Yes, in that case, when watering gives you calcium carbonate, it is insoluble. You're applying it on the surface, and the pH goes up in the soil. From going to 6, you begin to 7.5 or 8 in pH, and that brings different problems and a different way to absorb nutrients from the soil. So that's different. So it's not acidifying the soil, but the water is actually playing against you. And because it's insoluble, it also makes the structure of the soil more susceptible to compacting. Yes, just to say that urea does acidification. It is neutral, but ammonium nitrate is the ones that actually have protons. Another case, when you apply dolomite or calcite, the calcium magnesium doesn't correct acidity. It's the CO3 that corrects it. That's what needs to be incorporated. And the other thing that's important is the bioindicators, biosensors, something that goes through the lot and sees the roots, can tell you where compacting is. Yes, but in a plot of 100 hectares, to go with a shovel, you showed there at the beginning of the sowing, you can see the differentiated growth. And because the traffic of machinery is throughout the plot, the compaction is everywhere in the plot. So there was a difference in texture, what you showed. Just to clarify, so we don't have mistakes, but the same sensors, the roots indicate compacting of the soil. The soy that looks like a spidery web is the penetrometer is not the right implement, because when the soil is dry, you have mature soil. You have to use the shovel, look at the roots and that. Thank you. And urea does not produce acid. Okay, I wanted to ask, here, I am here. Yes, go ahead. Thank you for your presentation. This is alfalfa, I think, on the image. I wanted to know if you had experience of how does it evolve with regards to compacting, especially with that effect of extracting calcium, magnesium with the lowering of pH, how this influences compacting from the first year and in continuous years. And of course, also, we just have a picture. It's just a picture. We do not have an analysis for compacting on alfalfa.
Te hago dos preguntas. Sí. Una es,
one question is, how is, when you use EasyScan with regards to the yield map, this is a question. Is it similar? Because otherwise we would have other readings. You're speaking about decompacting. I agree that when the soil is dry, you can still see that indent. But what is the threshold for decompacting? Do you take a threshold for penetrometry and then a tip that I wanted to tell for everything, which is when you do mechanical decompacting, behind that you have to change your behavior. What I moved and generated is something I should maintain. So roots are fundamental. Those two first questions. What allows us to determine the diagnosis or the electromagnetic induction map is the features of the soil, or to project the yield within the plot. So if you sow the plot in the same way, the yield will be very similar to what EasyScan shows, because the productive features that the scanner gave us, if we do that on the yield map, it will have great projection. So to have these maps will allow us not to sow it in the same way, but to make the most of the variation that we have in the plot, to handle what's variable, and to get the best benefits of each of the environments that we have. The other thing that you were saying, once you do tilling, what is the parameter that we take? We generate these graphs for penetrometry knowing the variation of depth, and what we evaluate is what is the degree of humidity we had when we sowed and what the resistance is. So we don't take a single value, but when we do have more than 70% of useful water within the plot, if it's over 2.5 megapascals, the recommendation is to decompact it at the depth that the scan gave us and that we have corroborated with the scanner and with the penetrometer. And this goes hand in hand with management. We have to decompact and then change our behavior. Otherwise, the solution won't be long-term.
¿Puedo?
Sí.
Me animo a preguntar por lo.
I want to ask, with regards to what you said about compacting of forested soils. I work on the island, and now, yearly, they are doing different types of sowing. I don't have these tests with penetrometry or any kind of studies for soil analysis, but even with reasonable loads, which have always been, you can see, you see compacting even visually in my fields. And sometimes when you use 2 equivalents per hectare or agriculture, but it is feasible that it is compacting. And besides from the recommendations and the tips, all of this methodology of penetrometer and do the in-depth analysis, these are very different soils, as you were mentioning. But is it reasonable to assume compacting with a low load? We just use rollers, no heavy machinery, really. We don't use that. We're talking about forest grazing. Maybe they're low loads, but the conditions of the load when they are ongoing, and we have periods of rainfall, periods of having the animals being there, if there's going to be always areas where compacting exists. I think what we said at the beginning, the ideal thing is to do a diagnosis, to go there and to do the infiltration test, which is easy to do, and penetrometry is also easy. These are diagnostic tests that you can go to the field and take those samples and have those results within a day.
¿Se escucha?
Buenas tardes.
Good afternoon. Alfredo de Alberti from province of Buenos Aires, 200 kilometers southeast from Buenos Aires here. When you spoke about the causes for compacting, the transit of agricultural machinery and cattle. In the case that we have in the Pampas, not in the last 3 years, but before, we had many cases of 22% of compacting when the soil is wet. And in an area where we have where we had sandy loam or loamy sandy soils, when we have lots of white soils, what is the positive balance throughout the years with the contribution of sulfur and phosphorus and organic matter without the need to go with mechanical decompaction? For example, we have 700 kilos of less wheat with a harvest of soy that year, and 3 years later the decompacting disappeared because once again we had wheat in rotation and we no longer had a difference. So you're speaking here about Córdoba, Santa Fe, which are pretty different to Pampas. But I wanted to know whether you have measurements of observations in this province and what you have indicated, whether with biological decompaction and rotation crops it is enough, or whether we have to do mechanical decompacting when it comes to machineries or excess livestock. I'm not talking about tillage.
We do not have any experiments or tests, but I go back to what I said at the beginning. The degraded soils are more susceptible. Soils with the characteristics you mentioned, with good levels of organic matter, loamy, sandy soils or sandy, loamy soils, they have a better responsiveness. But if you have compacting at a certain depth, if compaction is higher than 2 megapascals, the roots by themselves will not solve the entire problem. They may help, but you will not achieve decompacting only with roots. If there was treading on the soil, and this created compacting, because we would need to understand if the soil is really compacted. You see the appearance of trodden soil, but you don't know whether it was fully compacted. Perhaps it is just trodden soil, and maybe this is one characteristic that will be reversed 1 year later. It depends. When you have degraded soils that are loamy sandy or sandy loamy, and if you don't have organic matter and microorganisms are at very low levels, perhaps some hardness will end up being compacted. But when you have good organic matter, perhaps it will be restructured rather than compacted. But I do not have any specific